Good evening to all, and my idea for this lecture, the lecture series, is basically to introduce with the plasma physics, and moreover, I would like to introduce everyone to the plasma cosmology, which is like very controversial, it's very relevant field. So, but the thing is, just jumping to the plasma physics or plasma cosmology without understanding basics will not be like fun, and the later on the journey will be become very complicated and all. So that's why I plan to like begin it with the basics first. So when we think of plasma, so what comes very first is a glow discharge, and this glow discharge tube, the different IV characteristics and different fundamental, and then with all this we find with all this we used to we used to understand the higher concepts in the plasma physics. So basically with the help of this glow discharge we are gonna formulate the principles for a higher very well known equations in physics such as Paschen's law, or it is a Saha equation. So my idea of this whole talk is to just get to know with all these why is diversity in the plasma physics, first thing. And another thing also, obviously goes very well understood that you can't get to know and get to learn whole field of plasma just in 3 hours of lecture. So what I will try to do, I will just try to give you an idea. I will try to introduce everyone with the thought process, okay, how actually the plasma field is, because I think till UZ in our country, like till UZ, we are not introduced to this field at all. Like there is no paper offered in nearly any universities or colleges which talks about in the UGs. So my idea is just to get to know this field, and later on you can decide, okay, what you want to do in the field and not. So to begin with, am I audible, right?
Yeah, Samarth, you are.
Nice. Actually, this created a lot of confusion to me. Okay, so to begin with, I will just go with the idea of the glow discharge. And you might have came across this glow discharge with a like when you read of this Thomson's experiment where he first find this cathode rays, and then further he get to the idea of the electron, or whether it's anode ray. So you must have came across this glow discharge. But the thing is, my approach to this glow discharge will be more theoretical and rigorous. I will try to get you introduced to the different electric field, different potentials which we can observe in this glow discharge. So basically, what is a glow discharge tube? So it's not just a cylindrical tube where they are which is where the gases are present at a very low, and then there is one cathode and one anode is there, and this cathode and anode is connected to high tension battery. So here basically in image high tension battery is not being shown, but high tension battery is basically you can think of something high power battery, and then this is pretty much more vacuumated, and the gases is being gases is very rarefied, like they are very gases are present but at a very extremely low pressure, and that is being modulated with the help of the vacuum pump which is acting here. So when you connect it with the electron and when you connect these electrodes with the high tension battery, and when there is a right gases, when I say the right gases is being filled, like here the whatever the gases is there, it should be something right gases. Just mind my word, right gases. So when the right gases spin and connected, and it is the electrodes are connected to a high tension battery up to particular voltage, what you will observe? You will observe a glow, and the glow is something which is like experimental. You can observe in the laboratory, like for the advanced plasma laboratories, nearly for all master level students. So yeah, you can observe this type of glows. Now the thing which comes in mind, okay, these are the glows, then why the two colors are different, and why these all things are not different. So this idea is there, and we will try to understand the different reasons in the globe. So first what we will do, we will look for the IV characteristics, and from the IV characteristics we will try to get to introduce to a newer concept. So I'm changing a slide to the next slide, that is typical current voltage characteristics for electric discharge of gases. So in this what we will do, so in this IV characteristics, what we will do, like they are the typical current voltage characteristics for electric discharge of gases. So in this what we had, like we had that apparatus, and here what we are doing, we are not doing some any we are not doing much thing. We are simply plotting a graph between the current and the voltage which we are getting in that discharge tube, what I had shown you previously. So now basically what you can do, so like when you do an experiment, you can, when you do an experiment, you can basically find this type of curve, and there are many regions marked like A, B, C, D, E, F, G, H, I, and J. Then you can broader distinguish between dark discharge, glow discharge, and arc discharge. So this IV characteristics is very important because it helps us to classify and like different discharge regions like dark discharge, glow discharge, and arc discharge, as well as it introduces you to some theoretical concepts, like you can get to know about the avalanche breakdown, the Thomson Region breakdown, then what is corona. You can get not that corona virus, but there is like physical corona, physics, where there is a corona in physics too. So you can get no idea of the corona. Then you can also understand with this curve that okay, what is the normal glow and what is a normal glow. Then there is again non-thermal and thermal arc. So what I will do, like I will try to make you guys understand, okay, what is happening in this curve, like why you are getting this kind of weird curve, like there is no straight line, there is no as such. So why you are getting this type of plot, I will try to let you know, and I will try to also let you know what is the mechanism happening behind it. So the thing is, we will begin with the A. So now before let me explain the reason for this curve, you should also notice one thing. See, the x-axis is a current axis, or this axis, this is a current axis. And if you see the current axis, the current is being represented, and the coefficient like 10 power minus 10 to 10 power minus 8, then 10 power minus 6, 10 power minus 4, minus 2, then 100 and 1000. So you can see how this is being grouped and categorized. So you can see that there is a variation of lot of current. Like you can see, if you talk of the orders, so the current is varying nearly in the 10 to the power 13 order, because minimum is 10 power minus 10 and 10 to the power 14 order. Minimum is 10 power minus 10 and maximum is 10 power 10,000. So the 10 power minus 10, the current is varying from 10 power minus 10 ampere to 10 power 4 ampere. You can understand, okay, there is too much variation. So now you can get an idea of this variation is happening and why there is a variation. And this voltage, I'm not fixing values, but you can assume, okay, this voltage values are generally high enough in the sense it's not like some 200 or 300 voltage. It goes beyond that. It goes beyond 300, and this voltage values is not specified here because it varies for gases to gases. So that's why it's not specified. So now what we will do, we will try to analyze, okay, what is happening between each and every point. So we will first try to begin with the point A. Okay, what is happening at point A? Hello, am I audible? Yeah, nice. So what is happening at a point A? So now in point A, where I had mentioned point A to point B, this is the one reason where you can see that curve is little bit exponential curve. So this in this region, what happens, basically a background ionization happens. So now what happened, when I have a two electrode, right? One is anode and one is cathode, another is electron. So what happened initially? What happened, due to some, now you just consider due to some magical reason, suddenly one or two electrons comes out. I will tell you what this magical reason is, or reason why this electron is coming out. So just imagine, like, due to some magical reason, what happens, like one or two electrons is coming out, and the electron which comes out of the electrode, we call it as a cosmic electron. So due to some magical reason, a cosmic electron used to come from the cathode out. Now once the cathode, like the number is reasonably very less, and this number of cosmic electrons which is coming out of the cathode is like reasonably, it's very less, it's actually very less. And what does it do? That cosmic electron, we get some very small amount of current. So that current is basically A, and that current is basically A and B. The current you observe in the region A and B is because of the cosmic electron which is coming out of some magical reason. I will tell you what that magical reason is in the last part of the slide. Basically, that magical reason is nothing but a Saha equation. So out of just for you think that because of the Saha equation, one cosmic electron is coming, and that cosmic electron is causing some, some now current, and that current is nearly like very less, that is in order of some 10 to the power minus 10 to 10 to the power minus 8. Now what happens once the cosmic electron comes out? What it does, it gains kinetic energy. Why it gains kinetic energy? Because the electron is present between two electrodes, and you know that charged particle accelerates in the direction of electric field. Obviously there is a potential difference between two electrodes, that is anode and cathode. There is a potential difference, and due to potential difference there will be electric field, and due to electric field, whatever the cosmic electron is coming out, it will be getting accelerated and it will gain a kinetic energy. Now what will happen? Now there are two things can happen. One thing is that the cosmic electron which just came out of the cathode, it can collide to some another ion, or it cannot collide to some another ion. So now the thing is whether it will collide or it will not collide. That is like and another thing is, okay, how the collision process will be. So if you can consider, like, okay, the electron is being accelerated to the electric field, and if there is a lot number of gases, background ionization, what does it mean? Just give an idea. Background ionization is the ionization of the background gases. I told you, like in discharge tube, we fill certain gases, and that gas is basically at a very low pressure. So that background ionization means that ionization of the background atoms and molecules which is present in the discharge tube, and that background atom or molecule is nothing but the gases or the gases which we fill in discharge tube. So when this cosmic electron out, what it will do, I will just show it on this all this thing in the next slide. So just you have an idea. So what it will do, it will collide to this molecules of the background atoms. Now once this cosmic electron will collide to the background of this atoms, what it will do, it will lead to the ionization. Like it will further ionize this background atom. So this is the process, this is the basically background ionization, and that will start from the point B. Now once the electrons are being created, what they will do, since there is electric field, all this electron will be swept. Electron will be accelerated toward the anode. So all this, and due to that, and all these electrons will be, when they are accelerated toward the cathode, there is no charge being left, as these cosmic electrons are created in a very less number. So that will what that will cause a constant amount of current. Why this constant amount of current is there? Because there is no new charges being created. Now once what will happen, for a certain amount of time, they will be like, even the voltage will be increasing. You are seeing the voltage increasing, but the current remaining constant. Why this constant current? Because there is no new charge being generated, and you know that current is directly proportional to charge. Like if there is more number of charge, more current will be there. So till the point B to C, there is no new amount of charge being generated due to any reason. That's why there is a constant current. Now this regime of in the IB characteristic is known as a saturation regime. Now you reach at point C. Now what will happen point C? So the difference between point B and point C is like the voltage is very high, like at comparatively high. Like at point B, suppose if the voltage was some 500, voltage, then at point C the voltage must be like some 1500 to 2000 voltage. Now obviously you can think that okay, whatever the electron, cosmic electron which was present here, which was present here, it will be having at a voltage V1, that it will be having at voltage V1, and that voltage is lesser compared to this point. Now what will happen? Now since the at point C the electrons, cosmic electron which is generated, it has been higher voltage. Now if that means that the kinetic energy will be more, because we know kinetic energy is equal to E into V, like potential V. So V is the P here, the V is large compared to this point. So whatever the cosmic electron present at point C, they will have a very high kinetic energy compared to this point. Now once they have a higher kinetic energy, again they will be like this background ionization will happen. Like background ionization will be occurring like always. So once they will be again these cosmic electrons will be colliding to the background atoms, and they will creating a further charges, further ions and electrons. And when this further ion electron will come, and this due to that again the current will be increasing, because the new number of ions and create ions are being generated. Now again I am keep on increasing what my voltage. Once again I am keep on increasing my voltage till point D. Now what happens point D? We have a two pathway. One is a breakdown pathway, another is a normal flow pathway. Now what will happen? Now the thing is, now I have a two things, because when I am ionizing my background atom, I am getting electron as well as ion. So what will happen? Now these ions will be getting, this ion will also getting accelerated. So if the ion is getting accelerated and further it is colliding with another atom, like there are a lot of atoms, this ion is getting accelerated and colliding another atom. So that will lead to the what? That will lead to the further electron, ionization. That one ion. So till this point, like till point D, only the electron was getting accelerated and colliding to another atom, and that will be ionization. But from the point D, both after like ionization of one atom, both electron and ions being created. Now after point D, both ions and electrons are getting accelerated and they are colliding. So now what will happen? This ion will also help to ionize the background atom, as well as the electron which is being ionizing to the background atom. So now that when this ions get when this ion get here ionize another atom, there is another electron which is created, that is known as a secondary electron, which I will show you how in the next slide. So that secondary electron is being generated, and this this path you will get because of the secondary ionization, and this path you will get because of the cosmic electron ionization. So due to that, you will come into the glow discharge region. In glow discharge region, nothing but here the just like whatever the discharge is happening, the gases, you can actually see it. Like you can as in my image, it's shown that you can basically see from the eye, and the current is also pretty much current is also like strong enough, that is more than from this region to this region. So this region will be glow discharge region, and in this there is another electron which is coming to the picture. That is what happens, that is a second electron. So now you have a cosmic electron in this region which is being ionizing. Here in this region you have a secondary electron as well as a cosmic electron. That's why you can follow the curve like this, and I will about the curves. I will keep on referring to this IV characteristics throughout my slide, because that's very important. So now once you come now that because of the ions, now again it will getting this accelerated because of the potential, then again it will collide, it will further ionize. So this process will keep on going, and you will understand the theoretical background of this process in the Paschen law. So that's like pretty much at the end of this talk. So now what will happen? Now for now you just think that okay, ions are also ionizing by creating a secondary electron. Then I had already a cosmic electron, so now I have a two carriers. So because of that, you comes to the glow discharge region, where the current is like minimal, like not minimal, it's like at least appreciable to the experimental level, that is 10 power -4 to 10 power -2 ampere. So now what will happen? You come into that again, if you keep on this process going, then you will come into the arc discharge where the current like increases so much, that is like from 1 to 10,000 ampere current. And why this current is like increasing so much? That is because you have a third kind of electron present in this coming to the picture, and that electron we call it a thermoelectron. So in this region you have a cosmic electron, or you can say primary electron. In this region you have a cosmic electron plus secondary electron, and in this region you have a cosmic electron plus secondary electron and plus a thermal electron. Now how this thermal electron is getting created? So the simple answer for this is the thermal electrons is getting created because of the thermonic emission. And what is thermonic emission? Well, as I told that since in this region, in the glow discharge region, you have both primary electron and secondary electron. And now when this primary and secondary electron is there, they will be accelerated. And once they are accelerated, they will reach to the anode, and they will be, or basically they will be, the electron will be reaching to the anode, and the ions is also there. So ion will be reaching to the cathode, because positive goes to negative, negative goes to positive. So the ions will also go to the cathode. Now what will happen? These ions will start hitting to the cathode, and once the ions start hitting the cathode, what will happen? It will increase the temperature. You know, if you keep on beating, the temperature will rise, right? The simple idea. If you keep on beating, the temperature will rise. So when these ions keep on hitting the electrode, the temperature of the electrode increases, and because of the high temperature, there is a thermonic emission, like electrons coming out of the electrode because of the increase in temperature. So you have another electron present here, that is your thermal electron. So you can see, you can have roughly an idea that in the dark discharge there is only one kind of electron present, that is your primary electron or cosmic electron. That is coming because of the Saha equation. Then here in glow discharge region you have two kind of electron present, that is one is primary electron or cosmic electron, and another is the secondary electron. How the secondary electron is generated? Secondary electron is generated because this cosmic electron is, you can say secondary electron is generated because of the background ionization. So now now in this region what is happening? Now because of the ions, it is hitting to the electrode, and due to the electrode hitting, the temperature is rising and it creating a thermonic emission, and due to that another kind of electron coming into the picture, and that is a thermal electron. So here you have a three kind of electrons and responsible for the current, and that's what is being very much justified through this curve. Like in this curve, there is only single type of charge carrier, that is electron. So you can see that current is very small. In this region, you have a two kind of two charge carriers, that is secondary electron as well as a primary electron. So current is pretty much high. And then in this region, you have a three kind of current carriers or charge carrier, that is primary, secondary, and thermal. So you have it like now current is so much high. So this is the basic idea. Now I will try to give the this is basically intro slide to my all topics which I'm gonna speak on today. So that's why I spend a little more time, because you have an idea, okay, what is being. So basically what I will try to do, I will try to explain these terms with different theories, approach, and ideas. So now moving to next slide. So this is a better picture of it. So now this is, suppose this is not a cylindrical tube. Suppose this is some region where this cathode is, anode is there. Okay, this is the first picture I'm talking. So the anode is there, which is connected to the high tension battery, and then there is a pump, to decrease the pressure. Now because of this some magical reason, what happens? That magical region is basically Saha equation. So because of this, till now I hadn't talked about Saha equation, so I will say due to magical reason. So due to some magical reason, one the cosmic electron is coming out of this cathode. Now what is happening? This cosmic electron is coming. And now since there is a lot of this is the case when I'm not decreasing the pressure. So when there is a lot of atoms present in the region, so what will happen? This cosmic electron will collide and it will lose energy, and so there is a lot of things will collide with and it will lose energy. So it will know of importance. So that's why what I will try to do, I will try to decrease the pressure so that I can reduce the chance of collision and hence the process of decreasing energy. So what will happen? This electron will at least collide to one of the background atom with a high energy because it will getting accelerated toward the anode. So once this cosmic electron collide with one of this atom, this atom, what will happen? An electron will be coming out and ions will be coming out, right? So what will happen? Electron will coming out and one electron will be coming out and one ions will be coming out. Now further this electron which is here, that is your secondary electron which will coming out of the collision, right? So I think now idea of the secondary electron is more clear. So the electron which will coming out of this collision, that will be your secondary electron, and then the ion which is there, now further it will accelerate to this direction. Suppose this collided here, an electron came and this electron came and here from the ions came, and then this ion will be accelerated in this direction towards the cathode. Now this ion will further collide with this cathode, and due to repeated collision there will be temperature being increasing, and due to that there will be thermal emission. So this is the rough picture what actually happens between the inside of the discharge tube. So now we will further go and see this is nothing but that all theory is written in the kinds of work. So I will send you the slide. I just added this page because if I send you slide and you are referring, you should have an idea. So that this is the Thomson region at that first region, that is Thomson region. Here you can see a tiny current flow initially due to a small number of charge here, and then you can get normal glow region, normal glow, or basically this glow region, I forgot to add this. This glow region is basically divided between two parts, that is a normal glow and abnormal glow. So this glow region, what is difference between normal glow and abnormal glow, we'll go through areas. So when the enough electrons produce sufficient energy to generate the same number of initial electrons, the discharge becomes self-sustaining. So one of the important thing here is here from the normal glow, the discharge becomes self-sustaining. It means that what it actually means, I will try to cover that in the Paschen part because that is a portion of that. And here for now you just remember that okay, in a normal glow the discharge becomes self-sustaining, and the gas begins to glow now, and the voltage drop accompanied by a sharp rising current. That you can see from the IV characteristics which I shown you. So, and there is a abnormal discharge also, that is basically kind of abnormal glow. So further now what will happen, further increase in power result in both higher voltage and cathode current density level. The abnormal discharge regime has now been entered, and this is operative domain for sputtering and other discharge process such as a plasma etching. So what will happen, what is the basic difference between this? In normal glow and abnormal glow, normal glow you will not observe the sputtering and the plasma etching, and that I will cover this sputtering and plasma etching in my second lecture. So but for now you just remember that okay, in normal glow you will obtain this, but in normal glow you will not. Then arc, I just told you current will be very huge even for the small change into voltage. If you see, and one important thing to notice from the IV characteristics, here you see the current is in arc discharge region, the current is changing very rapidly even for a very small change into the voltage. The voltage is changing very small, but even the current is changing too much, from 100 to 10,000. So that is the characteristics of the arc discharge region, that in the arc discharge region you will go rapid change into current even very small for a small change in the potential. And one of the place where you observe this arc discharge region is nothing but your lightning. So when lightning happens, actually people says that okay, in lightning what will be there will be lot of voltage, but this is not fair enough to say. If I ask you what happens in lightning, whether the current is high or the voltage is high, so you can't say that okay, you will not say that voltage is high you will say that current is very high, like the current is very high, not voltage. And why this current is very high? Because you have a three kind of charge carrier present, that is three sources of charge carrier. One is electron, one is your cosmic, another is a secondary that happens because of the Thomson breakdown and avalanche breakdown. I will cover what is this avalanche breakdown and Thomson breakdown later. And then you have a thermal electron. So these three kinds of electron make a very high results into the very high current. So this is the basic idea of the IV characteristics. This IV characteristics is very important, and we will keep on using it in throughout. So that's why it is the first thing ever taught in the plasma courses, because that's something transition that help you to transit from your gases, the ionized gases to the plasma. So further we have is my voice audible?
Yeah.
Hello?
Yeah, you're audible, Samarth.
Yeah, is perfect, right? Not breaking too much, right?
No, it's all perfect.
Yeah. So now what we'll do what we'll do after understand having a little bit idea of the IV characteristics. What we will try to analyze different reasons which we can see in the glow discharge tube. So basically, if you observe, this is basically a lab picture, and this is my lab picture, and in this lab picture, you will if you do an experiment on the this very first experiment of the glow discharge tube, and you will see something like this. So as you can see that you are not seeing just one color of light or one luminosity of light, or if you see this picture enough, then you can have an idea. Okay, they are different regions are present, or different different columns kind of thing is being present in the picture tube. So why this different column is there? Okay, if they are different column, okay, what are the properties of them? So that it create a lot of questions if you see this. So what is basically done. A picture tube, a glow discharge tube has been classified into a different region, and all these regions you can be seen here. So that is cathode, then you have a Aston dark spaces, then you have a cathode glow, then you have a negative glow, then you have a Faraday spaces, then you have a positive column, then you have anode glow and anode dark spaces. So again, there is a pretty much detailed explanation, but I will give you brief idea, okay, what these different regions are, and why they are like this, and why the current density is happening like this. So as if you want to read, you can read that Aston dark space is a very thin and contains both low energy electrons and high energy positive ions, each moving at opposite direction. So this Aston dark region, which is present just after the cathode, it is one of the it's one of the very thin region. And as it mentioned, it contains both electron. So this basically fogging me, because this initial part is more theoretical, and the plasma part is more computational, or you can say more mathematical. So you have to give some time to understand the concept. Then only you will be able to further enjoy it. So this region is basically Aston dark region, and this region is formed because here both ions, as I told that ions in the other characteristics, that ions are generated and they move toward the cathode. So in the Aston dark region, there is both electrons and ions present. So what will happen, I will just tell you why some regions is glowing, and why some region is not glowing, why some region is dark. So understanding that is more important than reading about all these reasons. So if you get time, I will refer you, or you can read it by yourself about different reasons, but I will just tell you, okay, why here you are seeing dark, why there is a positive column, why this is happening. So what will happen basically, as I told, from the cathode, the electrons will be generated, cosmic electrons are generated, and cosmic electrons will have initially a very less amount of energy. Now, as it moves toward the anode, the cosmic electrons, as it moves toward the electron, what will do, it will ionize the background, and once it started ionizing, what will happen? There will be like a liberation of, the electrons will be coming out, and the energy will be, along with that, some amount of energy will be liberated. And once the energy is being liberated, that's what we will see in the visible region. So that energy which is being liberated here, because of the ionization that is being here, that is your cathode glow, and that energy which is being liberated, you see, and that is basically, this is very big. Why this is very big? Because initially electrons have a, very less amount of energy, because it has, we know that as kinetic energy is like because of the velocity, and as more distances will travel, the more velocity it will acquire because of the acceleration, right? Because it is accelerated in this direction. So here that the kinetic energy of the cosmic electron is pretty much less, and because of that, the glow is big. As you can see here, the glow is the big. And once again it ionizes, the cosmic electron ionizes nearby an atom. What will happen? The electron will lose, the cosmic electron will lose all its energy. And that's why you are seeing the white region, basically that is your dark region. So you can see that it is a lighter dark region. Why this is lighter dark region? Because electron has loses all its energy, and then due to that will not able to further ionize, and not able to further ionize means no amount of energy will be liberated, and you will see pretty dim or dark region. Now what will happen again, in this region electron will again get kinetic energy because it is accelerated in this direction. So because of that, it will further ionize the background atom. So once it is started background, and this dark region is nothing but cathode dark space, you can see here. And then again it will gain a kinetic energy, and it will start again ionizing the background atom. So you will get a negative glow region. And again, once again it is started ionizing, it will both ions will be created here, and the secondary electrons will be created here. But these ions and secondary electron will be not having enough energy to ionize further. Then again, but they will be charged, right? They will charge. Then again they will be accelerated, and due to this acceleration, they will further ionize. So this process will keep on going throughout, and due to that you will get a different glow regions, different dark regions and glow regions. So the idea is simple, that the idea is cosmic electron will be birthing due to some magical reason, and due to that it will further move, then it will ionize, then again it will lose energy, again it will move, again gain energy, then again it will ionize, and due to that you will get a different glow regions throughout. So this is the idea, and that's how it is being divided, like the picture is being divided. But that this basically, as a physicist, the physics is not involved in this classifications, because that is a observation, and that can be observed, and that can, this is where the lucky people say, like Faraday's space. This reason is named after Faraday, because he was able to observe. So that's not too much of physics here. So we can move to next slide, and the same thing goes on here, different regions you can read from it. So the actual physics involved here, when you try to understand the functions of that, current, how the current is varying throughout the region, how the potential is varying throughout the region, how the electric field is varying, how the charge density is varying, and current density is varying. So and now what will happen, as you see, the first curve here, I had drawn a few curves, that is luminosity curve and potential curve, field curve, space charge density, and the current density, and how this varies across these regions, that is being shown. So now you see that luminosity curve is like this. And why this luminosity curve is like this? So I'll just in these curves I will just try to give a different bit idea, okay, how you are plotting this curve, or how you are getting this curve. So as I told that luminosity is because of the ionization process. Due to ionization, some amount of energy is being liberated, and that comes into the visual region, and due to that you are able to see. and more the energy liberated, more will be the luminous intensity, because energy is directly proportional to intensity. So due to that, here I think this pretty much being understood, because why this reason is this is pretty much why the luminosity intensity is varying throughout the region, because as I told, the kinetic energy will be gain, lose, and this process will go on. But the thing which interest people, that okay, out of all this region, most intense region is this cathode region. So as I written that in the cathode region there will be fewer number of particles, which result in lower potential. The charge density move as we this is not part. So here I wanted to tell you that the most amount of the luminous intensity is that the most luminous intensity is in this cathode region. Now the question is, okay, why in this cathode region the luminous intensity is very high compared to this compared to other? So that can be because most of the ionization, like as I told, in this region the electron gains maximum energy, because after losing energy here it gains maximum energy, and after collision the energy of electron is maximum in this region. So often it's like the energy liberated after collision is pretty much high here. That's why the intensity is high, and other thing that is barely like understood automatically. So from my last talk. So in this, like I will like give a considerable amount of time explaining like, okay, why you are getting these charges densities, and how you are getting this potential curve. Just excuse me for a moment. Yeah. Okay. I just took a break, and now I will talk on the potentials and field, like how the potential is varying, how the field is varying, and so we can understand like the potential, what basically equation which is playing an important role in this is a Laplace equation that is dou square V is equal to rho by epsilon naught. So in this reason, the potential and the charge particle, or the charge density is being related, like rho and potential is related. So in the cathode region, in this region, there will be fewer number of particles, which result in lower potential. The charge density move as we move toward the anode. The charge density, like here, the charge density will keep on moving as we move toward anode. Why this is happening? That's because as you keep on moving anode, the like more number of like primary, secondary electrons will come into the picture, as well as the ions will be coming into the picture. So as you move toward the anode, the more number of charged particles keep on coming into the picture, and due to that charge density is there, and then charge density will actually, it's chain density, no? It's charge density. So because of that, this charge density will be increasing, and you know that according to Laplace equation, dou square V is equal to rho by epsilon naught. If the rho is increasing, the potential will increasing. So that's why you can see this curve, as you are moving toward the anode, the potential is increasing. Now, now if you draw this potential curve, then you can very easily find the field curve. And how you can find the field curve, that is like electric field is near. We know that electric field is a negative gradient of potential. So due to the high potential gradient from cathode to anode, we get a higher field at cathode and negligible field at anode due to constant potential. So like if you take the gradient of this, you will get this. Here you are getting negligible field because it is pretty much more and constant in this region, positive column region. That's why you are getting nearly negligible field. So the same goes with the charge density, space charge density. The space charge density is maximum at like here you are getting two kind of space charge density, positive and negative. And this is also true for the current density. Like if you further analyze in the same pattern, you will get different, about try to understand different curves. So So I'm not giving too much time on all this, because if you want to, this is just like to give you an idea, okay, what is happening inside the discharge tube. But obviously, if you try to detail work out on each curves, it will take a plenty amount of time, and it's like a different completed paper or course in the field, and you can like always try to come. So the idea is like why I'm talking on all this thing is that because in most of the like Indian universities I'm aware of these universities and institutes, what happens, this plasma physics course is never an elective paper. It's never a core paper. It's always an elective paper. If you wish to choose, you want to choose, and you can choose it. It's not a hardcore paper. It's a softcore paper. And what happened, like when we go from UG to masters and we see plasma physics, we are not aware out of it. Like we don't have any idea of what is happening in this picture. So my purpose of this talk is to give you idea of this whole plasma physics, like what actually happening in the paper, so that later on if you want to study in detail, you can obviously opt for it. So I also want to tell that this plasma codes have a lot of importance, and why it is important, because this is commercially this course is very much important for in a commercial perspective. Like you can have a startup, if you know physics, you can have a startup and earn a lot of money out of it, or even you can a different set of problems with a different approach. As my idea is to introduce the plasma cosmology. In the plasma cosmology, we are like interpreting the same problems. Like we all till now we have been interpreting whole cosmology with the idea of gravitational and electromagnetic force. Like with these two forces, we were interpreting a plasma and with these two ideas, gravitational force and electromagnetic force, we are interpreting till now whole cosmology. But when you get to idea of the plasma physics, then you get another tool, that is plasma tools, to interpret the cosmology, how it functions. So this plasma physics give you another tool to interpret whole system, whole cosmology. So that is one perspective why it is important. Another perspective why it is very important, that is it's commercially very much useful. Like if you want to, you can develop many life easing product which you can develop day out in your daily life with the plasma physics, with the idea of plasma physics, and you can use it, and that's really helpful, and you can get a lot of money. Like nowadays, not in India but in foreign, like many startups have been grown based on the plasma physics, and they are very rich now. So this is the idea, and like that's why I'm increasing. And today I thought that okay, people should be aware of this course. Now, as I told, like Saha equations. So Saha equation is one of the very fundamental equation for all the plasma physics, and explaining not only plasma physics. It is a very fundamental equation to express any kind of ionization process at the where the ionization of the gas to gas process. So the simple thing is like. So now the Saha equation, like there is two perspectives of it. One perspective is a theoretical perspective, and like, Acha Pukul, what is the maximum time which I can have? Like it's already 6. So further, how?
It's up to you. It's up to you.
Okay, fine. So let me see. Okay. Okay, what I will do, then I will split this Saha equation into part. Today I will talk about this mathematical perspective of the Saha equation, and then maybe tomorrow in my next lecture I can talk about the theoretical perspective of the Saha equation. Why this mathematical perspective is important? Because it will help me to understand the IV characteristics which I saw. So the Saha equation, like today I am talking on the mathematical perspective of the Saha equation. So basically, if you Saha equation, we all know it's one of the most wonderful equation in the physics world, and especially it is more important to explain the stuff the energy ionization in the stars, not only stars, but it is one of the very fundamental of the plasma cosmology, also very fundamental equation in the plasma cosmology. So this equation have a lot of beauties attached to it, but I always understand the fact that you can appreciate a beauty only when you know what thing which you are trying to appreciate. So today I will just try to introduce, okay, what is Saha equation, how it look like. So this like as the statement goes, the ionization state of gas in equilibrium at temperature T is given by a Saha equation, and like what does this equation is giving? What is this equation is giving? So the this is basically like if you go and figure out, it will tell you, okay, at temperature T, how much of the how much portion of the gas will be ionized. Like it basically at the end it just tell us about the ionization fraction of a particular gas at temperature T in equilibrium, and that is being given by this Saha equation. But that ionization fraction is not in this form. This is not a form of the ionization fraction. This is for this is a very discrete equation, and we need to further simplify this equation in order to get the ionization fraction. So like there will be separate Saha equation for each pair of J and J plus 1 of ionization set with each element present in the gas. Like this is this equation doesn't talk about the collective behavior of the gas. It talks about the discrete behavior of the gas, like where be considered the state of each and every gas, like whether each and every particle which is present in the gas. So this Saha equation is like talks about the each particle which is present in the gas. So in the case of hydrogen, like what is basically Nj plus 1? Like I think I should introduce you to the terms also. So basically Nj plus 1, Nj, Z, this is the number of charged particles, ionized gas present. So number of ionized gas present in the J plus 1th state, that is some J plus 1th state to the ratio in the Jth state is given by Z is the charge of that gases, that is to what is the charge present in the J plus 1th state, and then what is charge present in the Jth state. So that is K is nothing but K is a Boltzmann constant, T temperature, H Planck's constant, and 3 by 2 e power minus xa by k by t. So this is the basically how the Saha equations look like. Today I am just dealing with the mathematical perspective, so we will try to look the equation, different terms, and what is the simplest form of this equation. So the simplest form of this equation obviously come into the picture. So the simplest form of the picture comes into the picture when you talk about the in the case of hydrogen, there will be only one single Saha equation, because there is a single state possible for the Saha equation, that is the electron can be ionized. There is only one electron, so that electron can go. So there is only one ionization state possible. But for another gases, like for nitrogen, there are at least how much electrons are present. So that much ionized, like it can lose 1 electron, 2 electron, 3 electron. So different ionization state is possible. But for hydrogen, there is only one ionization state is possible. So assuming most of the hydrogen is in the ground state, then Z1 is equal to 2 statical weight of the ground state, and Z2 is equal to 1 ionized state in the ground. Then Saha equation. So this how this Z1 is equal to 2 and how Z2 is equal to 1. That is basically because of this statical mechanics, and there is something called sorry. So this as I told that this is the J plus 1th state and Jth state. So you can in hydrogen you can have either ionized, that is 1 electron is lost, another is like when it's the ground state. So like for that you have an idea that okay, if it is in a statical weight for the ground state is 2 and for ionized state is 1. So you just keep that value here, and that further equation can be simplified to this value. Now this is one part of the equation. So whether you can do another simplification, but simply what happens, like when we talk about the broader scale, when we talk about just try to understand that equation is the actually real equation of the Saha equation, but that is not, that is, sorry, this equation is the real equation, but like for most of the practical purpose of most of the calculation purpose, we use this modified equation. In this modified equation, Ni and N are respectively the density of ionized atom, and that is a neutral atom. So Ni by N, that is your ionization fraction, that Ni by N. So you can transfer this N this side. So Ni by N is the ionization fraction, which is equal to A into T power 1.5 A exponential ui kBt power 0.5. So this is like here all the terms are very much introduced. Ui is nothing but the ionization energy of the gas that is being required. So this is more practical equations, and we use this equation. However, this equation has been came from the previous equation, this equation, and this equation in the blue is responsible for this equation. And I will tell you, I will send in the group the detailed workout of this equation, how it is coming, how we can get this equation from that equation. So just try to understand this. This is the equation which is responsible for the cosmic emission of an electron, which I was talking the IV characteristics. So once this condition, now this is met, the gas started ionize. The particular gas is starting to ionize. So now I had just plotted this Saha equation curve for the hydrogen gases. Now the plot of ionization factors versus temperature of the pure hydrogen. Pure hydrogen in this is the ionization fraction, and this is the temperature. So as you see, like for initially relatively less temperature, the hydrogen gas is not ionized. It is not ionized at all. But as the temperature keep on increasing, suddenly the ionization happens, and at a certain temperature, that is some 10 to the power 5, there is a complete ionization of the hydrogen gases. So this is for the hydrogen gases one of the simplest cases. So you can appreciate that how the temperature is helping to ionize. So this is the plot and the corresponding curve, which you can do it in the Python, that Python NumPy. You can just type this curve and you can do it. Otherwise, there are a lot more other options, like best option is the MATLAB. To use MATLAB, and you can basically, if you use MATLAB, then by using MATLAB you can actually solve this equation from here to here by using just MATLAB, and then you can get a corresponding curve for it. So try to do it, and like we can take it as a reading kind of project, and try to interpret Saha equation with a lot of more rigorous mathematics. Now this was the mathematical idea about this Saha equation. So if time is there, then I can take another 20 minutes to cover this Paschen curves and Paschen law also. So is the time is there? Yeah. Okay. Sure. We can stop for today. Then we can talk about the Paschen and Towson mechanism, and then break down Paschen law and Paschen curve. This is that how I want to basically that IV characteristics which we saw initially, and how the Saha equation is giving me a magic electron, then cosmic electron we will see. I'll like try to understand some other day. So I'm stop sharing.